Good morning, everyone. In this webinar, I will describe some of the conclusions of the most recent regional seismic interpretation of the Southern Perth Basin and the 3D model built afterwards in the GoCAD software released in 2020. First, I'll give a little background on the geology and tectonic setting of the basin, and then I'll describe the geophysical and well datasets used. Then I'll show a few interpreted seismic sections and maps and go through the tectonic events recognised, and then I'll give a brief overview of the 3D model. The Perth Basin is a rift basin that lies to the west of the Yilgarn Craton, from which it's separated by the Darling Fault. To the west of the Perth Basin lies oceanic crust of the Perth Abyssal Plain, and in the south, the Dunsborough Fault separates the basin from the Yallingup Shelf and the Proterozoic Lewin Inlayer. This talk focuses on the Southern Perth Basin, which is an informal name taken to be the basin south of Perth. The basin's filled with Permian to Lower Cretaceous strata deposited in predominantly terrestrial environments, and onshore it's up to 12 kilometres deep. It's divided into several subbasins for the most part by large normal faults, which extend up to the early Cretaceous breakup unconformity. The Southern Perth Basin also includes Permian outliers on top of the southwestern Yilgarn Craton, such as the Collie, Boyup and Wilga subbasins. This suggests the Darling Fault wasn't the boundary of the basin during the Permian. In these subbasins, tilted Permian strata are truncated by the early Cretaceous breakup unconformity, as can be seen in this image on the left of a face in one of the coal mine pits at Collie. The Perth Basin is a result of progressive rifting between Greater India and Australia. The Southern Perth Basin formed part of the eastern Gondwanan interior rift, and within present-day Western Australia, it represents the southernmost extent of this interior rift. This means that this part of the basin did not see the major marine incursions as seen in the Northern Perth Basin and northwards. This has made stratigraphic correlations within the basin more difficult. One of the goals of the seismic interpretation phase was to refine earlier interpretations. This was possible because the most recent regional seismic interpretation was done in the early 1990s, and since then, new seismic has been acquired or reprocessed, and more wells and boreholes have been drilled. Stratigraphic information from a greater number of water bores was also used. Another goal was to see whether the tectonic events proposed previously for the Northern Perth Basin could be identified. Extension or rifting episodes in the Northern Perth Basin have been proposed for the early Permian, early Jurassic, and the late Jurassic to early Cretaceous periods. Seismic coverage in the Southern Perth Basin is patchy, with most seismic, especially onshore, being low-fold and poor quality data. In the study area, only one 3D seismic volume exists, which was acquired as part of the Southwest Hub geosequestration project near Harvey. The patchy seismic coverage and quality meant that drill holes and potential field datasets were needed to extend the interpretation. 24 petroleum wells were used in this study and tied to the seismic using velocity data from checkshot surveys or sonic log data. Important stratigraphic boundaries were re-picked in petroleum wells and other boreholes, as previous published correlations were too reliant on lithostratigraphic concepts and were time transgressive, making them unsuitable for seismic interpretation. Although this part of the basin has seen less drilling of petroleum exploration wells compared to the north, it is overlain by prime agricultural land and dense urban centres. The high demand for fresh water has meant the basin is dotted with many water bores and groundwater exploration holes, which thankfully are deep and penetrate below the breakup unconformity as they searched for the Jurassic Yarragadee Formation aquifer below. In addition, 4 deep holes, each more than 2 kilometres deep, were drilled for the Southwest Hub CO2 geosequestration project, and each with petroleum industry standard wireline logs and velocity information. The south of the basin saw much coal exploration, with many holes penetrating down to the Permian, especially in the vast shelf, where the Permian subcrops beneath the breakup unconformity. Although water bores and mineral exploration holes don't typically have velocity information, the stratigraphic information still helped guide seismic interpretation and well stratigraphic pics. 8 seismic horizons were interpreted, the ages of which were constrained by the biostratigraphy in wells tied to the seismic. These horizons for the most part form the boundaries of distinctive packages in the seismic and broadly correspond to the boundaries of some formations. These include the top basement, which itself is not a strong reflector, but is peaked at the base of obvious sedimentary reflectors. Above are the near-top Permian horizon, corresponding to the top of the Sioux Group, and the top of the lower Triassic Sabina sandstone, which together form a coherent reflective seismic package. The horizon above is the top of the Wonnerup member of the Lisua sandstone, and is of late Triassic Carnian age. It is a thick, relatively clean sandstone that on seismic forms a distinctive acoustically bland package. The early Jurassic horizon above is probably of late Pliensbachian age and forms the top of the more reflective seismic package above the Wonnerup member. This package is interpreted to include both the Yalgarup member of the Lisua sandstone and much of the Eneabba formation and time equivalent. The next horizon above is Middle Jurassic and most likely mid-Bajocian in age, and tops a package that is for the most part more reflective than the interval above and below. It's interpreted to lie close to the boundary of what is equivalent in age to the Katamara coal measures and the Yarragadee formation. The base Cretaceous horizon is a distinctive strong reflector offshore and corresponds to the base of the Parmelia group. Onshore it is very shallow and has patchy distribution. The lower Cretaceous break-up unconformity of probable Valanginian age is an obvious angular unconformity nearly everywhere except in depositional lows. As we are at the southernmost extent of Gondwana and have no marine incursions, the absence of marine fossils means we must rely on spore pollen biostratigraphy for the interval until breakup. This slide was prepared by my colleague Sarah Martin, who collated and reassessed the palynology reports of wells and water bores. New sampling and reassessment of old slides was also undertaken with the aid of John Backhouse. This ensured a consistent biostratigraphic zonation scheme was applied to all wells and water bores. Potential field datasets such as gravity and magnetics were also used to help constrain seismic interpretation, especially where seismic coverage or quality was lacking. Gravity datasets act as a rough guide to basement topography and can show the major faults with high displacement. Aeromagnetic data, such as the total magnetic intensity and in particular the first vertical derivative, can also help guide the traces of faults. The lower Cretaceous Bunbury basalt is a prominent meandering feature in the magnetic data. It was erupted as a series of discrete flows as Greater India separated from Gondwana, and coursed northwards through incised valleys along the Bunbury Trough and offshore. In places, the basalt highlights coeval normal faults that helped guide the flow of the basalt. Now I will go through some of the interpreted sections and maps which help illustrate the main structural elements of the basin. On the right is the two-way time map to the early Triassic top Sabina sandstone horizon. Cool colours show where the horizon is deeper. On the left is a composite west to east seismic line through the centre of the Bunbury Trough. The location is highlighted in red on the map. It shows deepening of strata eastwards towards the Darling Fault and the fold in the west which formed in the hanging wall of the Busselton Fault and which forms the trap for the Witcher Range gas accumulation. Next is a composite south to north section through the Harvey Ridge, which is a broad northwest trending uplifted zone whose origin is uncertain. Here the Upper Jurassic is absent, which made the Harvey Ridge an attractive site for possible CO2 sequestration in the Triassic Wonnerup member sandstone, as there is no possibility of leaking into the precious Yarragadee Formation aquifer. Here is a composite west to east seismic section through the offshore Vlaming subbasin and the onshore Mandra Terrace. Interpretation of the lower Jurassic and older strata offshore is extremely tentative, as there are no well intersections of this interval and few connecting seismic lines between the onshore and offshore areas. What is apparent here is that the offshore Vlaming subbasin has seen much more intense brittle deformation and subsidence, and complex hanging wall geometries within the Ballymena fault system. Some localised folding can also be seen in the hanging wall of the Darling Fault in the Mandurah Terrace. The hanging walls of all major faults have seen some folding, some of which are intensely faulted, such as this one adjacent the Ballymena Fault in the offshore Vlaming subbasin. Most faults have been drilled for petroleum exploration. However, it's interesting to note that some of these folds are smaller than the gaps in existing seismic coverage in some parts of the basin, for example, the Eastern Bunbury Trough, meaning there is the potential for further traps to be discovered. Various intervals within the Permian of the northern Perth Basin have been proposed to have been syn-extensional. In the southern Perth Basin, the basement to top Permian isopack only shows a significant thickening below the Harvey Ridge towards the Darling Fault. However, as the entire Permian section has not been penetrated in this area, it's uncertain whether this isopack represents only the Permian or includes an older section, which will be discussed a bit later. Although seismic quality is very poor in the Bunbury Trough to the south, no thickening is evident against the Darling Fault. In the western Bunbury Trough, however, a slight thickening of this basement to top Permian section can be interpreted against the Sabina and Bustleton faults. If Permian extension faulting is real, then it was likely a subdued event. As seen earlier, there is extreme thickening below the Harvey Ridge towards the Darling Fault. The section on the right through the 3D seismic volume next to the Darling Scarp shows a more steeply dipping package at depth, and even at 10 kilometres depth, a basement horizon cannot be picked. It's not possible to know what age these reflectors are, but are tentatively assigned a pre-Permian age and imply an earlier, possibly older Paleozoic extensional event. Here, this extensional event is expressed only as normal movement on the Darling Fault, although it can't yet be discounted that this more steeply dipping package is lower Permian and simply implies early Permian extension. For the Carnian to top Pliensbachian section, which broadly corresponds to the Upper Lesueur Sandstone Yalgarup member and the Eneaba Formation age equivalent, wedge geometries and obvious thickening towards the Darling Fault, and to a lesser extent the Bustleton Fault, can be seen in sections across the Bunbury Trough. An early Jurassic extension event was proposed for the northern Perth Basin in previous literature based on seismic interpretation. The late Jurassic to early Cretaceous Valanginian time is recognised as the main rifting episode that led to the breakup between Greater India and Australia. Based on the interpretation here, two syn-rift packages are recognised. The thickening pattern of the mid-Jurassic to base Cretaceous isopack on the left suggests the Darling Fault accommodated much of the strain in the southern end of the basin, and to the north its throw was transferred onto the Ballymena Fault system and offshore Bustleton Fault, allowing an equally thick package to be deposited in the Vlaming subbasin. The base Cretaceous to break up unconformity isopack on the right shows that at the onset of the Cretaceous the focus of rifting shifted almost entirely to the Vlaming subbasin, with rapid subsidence allowing a thick pre-breakup lower Cretaceous section to be deposited here in a very short time. Given published interpretations of oceanic crust isochron orientations, rifting is interpreted to be northwest-southeast oriented, and given that much of the strain at this time was accommodated on north-trending structures, we can interpret an oblique rifting regime. Therefore, a component of strike slip on these faults can possibly be expected. It's during this final rifting phase that most folds in the basin formed. Most folds are located in the hanging walls of the major faults, and possible mechanisms for their formation include rollover folding during normal displacement, or as products of oblique extension along fault bends or at relays. The Harvey Ridge uplift is proposed to have formed as a result of oblique extension, as it sits within the relay that developed at this time between the more active southern section of the Darling Fault and the Ballymena Fault system. In some lines offshore in the Vlaming subbasin, reverse faulting along the offshore Bustleton Fault can be seen, which implies an inversion event not long after breakup, or possibly later during the breakup phase. This seismic section and aeromagnetic image in the bottom right corner also illustrates well the character of the Bunbury basalt and the coeval normal faulting. In conclusion, the seismic interpretation shows the basin has a multi-phase rift and extension history. Up to 4 phases of extension can be recognised, the earliest being a possible pre-Permian extension event only expressed as normal movement on the Darling Fault, although this could actually be an early Permian event. There's also weak evidence in other parts of the basin of subdued Permian extension. The late Triassic to early Jurassic extension recognised in the seismic data may be related to the early Jurassic extension recognised in the northern Perth Basin previously. The final rifting phase commenced in the mid-Jurassic, seeing extensive normal faulting, especially offshore, and rapid subsidence, leading to breakup between Greater India and Australia in Valentinian time. Most, if not all, folds and domes formed during this final rifting phase as a result of either oblique extension or rollover folding on the major normal faults. The Darling Fault accommodated much of the strain during the late Triassic to early Jurassic and pre-Permian extension phases, as well as during late Jurassic rifting. It appears to be less important during the possible Permian extension and during the early Cretaceous rifting that led to breakup. Using the interpreted faults and grids, a watertight 3D model of the basin was built in GoCAD. The model is intended to be used for regional petroleum system and basin modelling, or for regional groundwater flow modelling. Given the size of the model, it's coarse in resolution, and some of the smaller offset faults couldn't be included, but the original higher resolution grids are available. Thank you for listening, and I look forward to discussing the basin further after the talk.